Good morning. We'll start with today. We'll start with the part 3 of chapter solution. In this video, we'll discuss Rault's law, ideal and non-ideal solutions, as we talk. So, moving forward, what is Rault's law? Rault's law states that for a solution of volatile liquids, the partial vapor pressure of each component in the solution is directly proportional to its mole fraction. Let's say in the solution you have two solvents. Red one is A and green one is B. So these are present in the solution. The partial pressure for PA is directly proportional to the mole fraction of the PA, the A component. Similarly, the partial pressure of B is directly proportional to the mole fraction of B. So, and the presence of the other volatile solvent also affects the partial pressure of the other solvent, since they both occupy the surface from where the equilibrium is maintaining with the equilibrium between the molecules in the gaseous phase and the solution phase. So we can say that for a solution of volatile liquids, the partial vapor pressure of each component is equal to the directly proportional to its molar fraction, and that P total is equal to partial pressure of A plus partial pressure of B, where PA is directly proportional to its mole fraction. When partial pressure of A, this proportionality sign is increased, then we write this P naught A into XA. Similarly, for P partial pressure of B, we will be writing P naught B into XB. And if we combine both of these two and put them in the total partial pressure of the solvent, then solution we will write P naught A into XA plus P naught B into XB. Since mole fraction is equal to XA plus XB is equal to 1, then we can say XB could be written as 1 minus XA. Substituting the value of XB, we will write P naught A into XA plus P naught B into 1 minus XA. Now, trying to solve this equation, P naught A into XA plus P naught B minus P naught B into XA. P naught B plus P naught A minus P naught B into XA will get P total. P total is equal to P naught B plus P naught A minus P naught B into XA. So that's how we'll derive some various forms that could be used in different solving different problems. So let us just first understand that P over partial pressure of 1 is directly proportional to the mole fraction of the component, and we'll remove the mole fraction, the proportionality sign by writing the P naught value. Similarly, for the partial pressure of 2 is directly proportional to the mole fraction of 2, and we can write the removing the proportionality sign in this manner. Thus, using the Dalton's law, this is the equation that I derived. If you had paid attention to the derivation that I did, in that derivation I try to derive this equation. Let me just derive it again for you. So we know that as per this Rault's law, total partial pressure of any component, let's say A, is directly proportional to the mole fraction of that component. Therefore, we can write PA is equal to P naught A into XA, that is mole fraction. Similarly, partial pressure of B is directly proportional to the mole fraction of B component. Therefore, partial pressure of B could be written as P naught B into XB. Since P total is equal to P total for the solvent is equal to partial pressure of A plus partial pressure of B. Substituting the values from above, P naught A into XA plus P naught B into XB as mole fraction of component A plus mole fraction of component B will give you 1. Therefore, you can write XB in the form 1 minus XA. Therefore, substituting the value of XB in the above equation, will get partial pressure of total P total is equal to P naught A into XA plus P naught B. XB could be written as 1 minus XA. Solving this equation, P naught A into XA plus P naught B, multiplying it inside, P naught B minus P naught B into XA. Taking XA common from here, we can write P naught B over here plus P naught A minus P naught B into X. Therefore, P total is could be written in this form. This is what which is written in the previous slide. Okay. Now coming to the why it is important to use Rault's law. Why it is important? It is important because let's say assume that we have a closed container filled with the volatile liquid. This is the closed container. Okay. So there is a volatile liquid that will sublime. After some time, due to evaporation of particles of A, will move a layer. Let's say the particles are present in this solvent and it will move. So some particles are present in the vapor state and some particles are present in the liquid state. And there is formation of this layer on the surface of the liquid. So then as time passes, the vapor particles of A will be in dynamic equilibrium with the liquid particles. Now there will be an existence of the equilibrium as the pressure the pressure outside is equal to pressure inside. At that time, some equilibrium will be maintained because of that there is a dynamic equilibrium between there is a free movement of the particles inside and outside of the solvent. Now, the pressure exerted by the vapor particles of A at any particular temperature is called vapor pressure of A at that temperature. P is temperature dependent. Now, vapor pressure is exhibited by all solids and liquids and it depends on the type of the liquids and temperature. Now, if we imagine that if we are adding another another liquid B acting as a solute. Now the molecules will be hindering the motion of this A outside and inside the two faces. So this will result in the B particles occupying the space between the A particles on the surface of the solution. As a result, for any given liquid, there is a fraction of molecule on the surface which will have sufficient energy to escape to the vapor phase. So, some particles on the surface have sufficient energy that will eventually go to the vapor phase. But since now we have lesser number of particles, the pink particles in this layer are lesser than the previous slide where there were more number of particles. So what this suggests to you? This suggests that this time, since because of the particles, the green particles are present because of the B, the number of the vapor particles of A in the vapor phase will be lesser. This will result in the lower vapor pressure of A. This suggests that, this tells basically, if you are adding some non-volatile solute to your solution having some partial pressure A, because of the addition of that solute, the PA will be reduced this time. PA will decrease because these green particles, the other solute particles, will hinder the free motion of the liquid or the pressure exerted by the pure liquid in the vapor. So, we can say that now if we assume that B is volatile as well, we will have lesser number of B particles in the vapor phase as compared to the pure liquid B. Therefore, we can say as a new partial pressure of each component A is given by the Rault's law depending on the concentration of the each component in the liquid phase. Rault's law says that let's say you have this beaker, 4 beakers you have 1, 2, three beakers we'll consider. This one contains liquid A, this one contains liquid B, and this contains A plus B. Liquid A will there will be formation of these red components and they will evaporate, exert a partial pressure of P naught A. P naught A, why? Because it is pure solvent. Similarly, when liquid B, the molecules will evaporate and maintain a dynamic equilibrium with the molecules present in the vapor phase, and the vapor pressure will be P naught B. This is for pure solvent B. Now in the case of A plus B, molecules of A are present, molecules of B are present, so there will be lesser molecules of A and there will be lesser molecules of B in the vapor phase. So we can say that PA, now the new pressure, vapor pressure of PA is the vapor pressure of the mixture and PB is the vapor pressure of the component B in the mixture. B in mixture, A in mixture. So we will say that P naught A is lesser, P naught A is actually greater than PA and P naught B is greater than PB. Thus we can say that the vapor pressure of the solution containing A plus B is equal to the vapor pressure of the A plus vapor pressure of the B. This is of mixture component A in mixture, partial pressure of component B in mixture. And since PA is less than P naught A, PA is equal to proportional to the mole fraction or the particles of the molecule A in the solvent. We can write PA as P naught A into XA. Okay. We'll substitute these values and you will get the same equation that we derived in the previous slide. That is, PA is directly proportional to the mole fraction of A, PB is directly proportional to the mole fraction of B, and we can remove this proportionality sign by writing partial pressure of the pure solvent A and the partial pressure of the pure solvent B. Thus, the graph below shows the pressure in the mole fraction of A. That means if more molecules of A are present, there will be, see, one is mole fraction 1 means number of molecules of A by number of molecules of A plus number of molecules of B. If number of molecules of B are 0, that means 1 by 1 you will be having a and this value Na over Nb will get cancelled and you will having a mole fraction of 1. That means if you are having a pure solvent A, that means in that case mole fraction is 1. You will be having a partial pressure P naught A. That is the partial pressure of the pure solvent. But in a case when you have mole fraction of B, where you mole fraction of B is Nb plus Na, where you have zero number of A molecules, that means pure B. In that case, Nb will be divided by Nb will give you value 1. That means if you have mole fraction B equal to 1, then that case the pressure exerted will be P naught B. That is because of the pure solvent B. Okay, and at that time if you say that here if the Na molecules are 0 and Nb is present, then the mole fraction of A will be 0 divided by 0 plus Nb. It will give you value 0. That means at that point Pa is directly proportional to mole fraction of A. Since the mole fraction is equal to 0, you will be having this partial pressure of A in the mixture as 0. Okay. Similarly, for B, if mole fraction of B is 1, that means it is pure B. In that case, the pressure will be the partial pressure of the pure solvent B. If the partial pressure of, if there is no molecules of B, that means mole fraction of B is 0. In that case, partial pressure P naught A will be the total partial pressure. When we combine these both graphs, we'll get this kind of graph. From Rault's law, it is evident that the mole fraction of the component reduces its part fraction, also reduces the vapor phase. So when we combine this graph, saying that if mole fraction is of A is 1, that means we will have a partial pressure P naught A. PA is equal to P naught A into XA. Since XA is equal to 1, you have partial pressure PA is equal to P naught A. Similarly, if you have XB is equal to 1, PB is equal to XB into P naught A, P naught B. XB is equal to 1, in that case PB is equal to P naught B. Okay, if you have mole fraction is equal to 0, then you have the partial pressure of B equal to 0. And if you have mole fraction of B equal to 0, in that case you will have a partial pressure of B is equal to 0. And the line in between defines the total pressure P total, which is equal to PA plus P no PB. Okay. Now this is the same graph that we discussed in the previous slide. Now we'll try to understand that what is the relation between Rault's law and its relation with the other laws. So Rault's law states that the partial pressure of the component A is directly proportional to the mole fraction of the component A in the mixture of volatile solvents. Thus, we can say that Rault's law is also quite similar to ideal gas law. That is, ideal gas law is PV is equal to nRT. The only exception of the Rault's law is that it applies to solution. So if you have read about the ideal gas law, we know that it assumes the ideal behavior of gases, which is intermolecular forces that are present between the dissimilar molecules is zero or non-existent. So meanwhile, the Rault's law assumes that the intermolecular force that exists between different molecules and similar molecules are equal. Rault's law can also be applied to non-ideal solutions. However, this is done by incorporating several factors where we have to consider the interactions between molecules of different substances. If we take a perfectly ideal system consisting of an ideal liquid and ideal vapor, we can further derive a very successful equation by combining Rault's law and Dalton's